Hello, everybody, and welcome to another wonderful day of physical chemistry. So today we're going to dive into that most commonly misunderstood of quantum topics, Heisenberg's uncertainty principle. So this is the classic adage that uh, the more you know about a particle's momentum, the less you know about about its position. And this essentially mostly stems from the ideas of wave packets. So as we saw before, if I have an eigenfunction of momentum, this will mean that I have a system that's traveling through space unidirectionally with an oscillating probability density. Now, the problem is if I do have an eigenfunction of position, because it's constantly moving, it means I have almost no information about the position of the wave function because it's going to go from here to infinity. Because again, if I have an eigenfunction of position, that means that, well, or eigenfunction momentum, it means that, well, I'm spread out over all space. So one of our classic solutions to this problem is I can go ahead and try and confine the particle to essentially a box by combining a superposition of two eigenfunctions of momentum, one going to the right, one going to the left. Their overall net momenta should cancel out. So I should have a stationary particle and I should have a distribution of density in the system. And depending on my functions, the exact position can be one of several options. But you'll notice in each of these cases, my position is still fairly spread out over the length of the box of interest. So I know a bit more about the position of the particle, but not too much. And again, I know that the momentum is one of two things. Now, it turns out it's actually possible to further constrain the position of a particle by adding in additional eigenfunctions of momentum. So if I start with, say, two wave functions, I can go ahead and get, say, a stationary particle. I add in five, I get to, and I am very selective about the additions and cancellations of my amplitude, I can actually get the system to mostly centralize around a given point. You go up to 21, and it tends to be very centralized. And again, this superposition of wave functions is called a wave packet. So you'll hear me say the phrase wave packet fairly frequently. And this is essentially just a way to describe a combination of eigenfunctions of momentum or a combination of various wave functions that may also be an eigenfunction of energy. And we do run into a slight problem because as I'm essentially localizing the system in space, what have I done to the momentum? If I've got 21 eigenfunctions of momentum, that means that my particle can have one of 21 different momenta, which means I know very little about the actual momenta of the particle. And this gives us a general rule, which is really the underpinning of Heisenberg's. And this is the idea: the more I localize a position, so the more wave functions I'm going to need in my wave packet or my superposition. By that very nature, I'm going to know less and less about the momenta. So can be quite a problematic arrangement. And this relationship is often expressed via the Heisenberg uncertainty principle. So here's it in its mathematical formulation. And essentially what it's telling us is that the uncertainty in the momenta times the uncertainty in the position has to at least be 1/2 h bar. So this is the minimum value. Now, that doesn't mean that it can't be much greater. There's plenty of ways you can know less information about your system. But the theoretical maximum, the best you can possibly know, say, the position of a particle with a momenta of 1 is going to be 1/2 h bar. You can't ever do better than that. And this, unfortunately, has a lot of implications upon, well, a lot of real measurements. So if I say I'm using an electron gun with a known momentum, I can only know the position of any particles I'm detecting to a certain extent. And this is just going to be inherent in the system, is that if I have a system with well-known position, it means that I've essentially temporarily captured a system that can go any number of different directions. So I know nothing about where it's going. And this is an important thing to kind of keep in mind when we're talking about when we're talking about wave functions. Is if I perfectly know the momentum, I have an eigenfunction of the system. That means I know, and I have zero um, uncertainty in my momentum. That means that I know nothing about my position, and vice versa. And this really helps solidify our understanding of quantum particles, so things like electrons and neutrons, as inherently kind of fuzzy in nature. We can never quite pin down exactly what they're doing because essentially they're always moving too fast and too unpredictably. Now, when it comes to the nuts and bolts of the Heisenberg's uncertainty principle, it's also very important that we know what we're talking about when we say uncertainty in position and uncertainty in momentum. So what we're really representing these as is the root mean squared about the property. In this case, since we're looking at momentum and position along a unidirectional x-axis, this means that it's going to be the root mean squared of these properties around that set axis. So in this case, when we're looking at the uncertainty of momentum, it's going to be the square root of the average of the squared momentum minus the average momentum squared. Now, it's really kind of useful to know that these two things, while they look similar, are going to be very different. So when we're talking about this average squared momentum, it's literally going to be applying our momentum operator twice to our wave function. Whereas when we're talking about the squared average momentum, this is going to simply be applying my momentum operator once and then squaring the result. So these are going to actually be fairly different properties. This first one is again called the variance, and we'll be spending a fair bit of time playing around with the variance for various systems as we go forward. And again, you can have variance of momentum or position or any number of other properties. Now, one of the things that I do want to make very clear is that this is all around a single unit axis. So it does turn out that you can actually perfectly know the position, let's say, along the y-axis and the momentum around the x. These two will be unrelated, as we'll spend some time discovering next time when we really talk about what's going into the uncertainty principle. It's also worth noting that while the uncertainty principle is most commonly known for position and momentum, it actually also applies to a number of different quantum mechanical operators as well. And we'll talk a little bit more about what it means for two properties to have inherent uncertainty with each other. For now, though, I'd like to kind of spend a little bit of time really showing how we can apply the uncertainty principle. So one of the classic applications of the uncertainty principle is looking at a particle in a confined space. So let's say I have an electron that's confined somewhere along a hydrogen-hydrogen bond. So this has a distance of about 0.75 angstroms. And I want to know what's going to be the uncertainty in the momentum if I have an uncertainty of about 0.75 angstroms. So we can essentially do this by setting up our equivalence. We can go ahead and divide both sides by the uncertainty and the position, as that's what I already know. And now I have the uncertainty, the minimum uncertainty in the momentum expressed as a function of h bar and the uncertainty in the position. Then what I'm going to want to make note of is that 1 angstrom is 10 to the negative 10 meters. Go ahead and put that in, let unit cancellation work, and we have the uncertainty of the momentum of an electron along a hydrogen-hydrogen bond. However, let's be honest, we normally don't think in momentum. So let's go ahead and kind of translate this into velocity. So in velocity space, I can get to velocity simply by taking my momentum divided by the mass of the particle. As I said, in this case, we're dealing with an electron. So I'm going to divide my new uncertainty of the momentum by the mass. And this gives me an uncertainty in the velocity of an electron of about 10 to the seventh meters per second. So while it may seem that, this is a fair bit of uncertainty in an electron, it turns out that this is actually pinning down the electron fairly well in space, as demonstrated by the fact that if I know the position even this well, which again is still less than an angstrom, it means I know virtually nothing about the velocity of the electron, as this uncertainty in the velocity is about on order of about 0.03 c. So yes, this is an appreciable fraction of the speed of light. Yeah, it turns out electrons move pretty fast when you combine them to a bond. And this is something important for us to kind of keep in context. So next time, we're going to be diving in a little bit more about what it means to not be able to measure two properties at the same time, as we dive into that fun mathematical concept of commutation. Till then, take care.